Hello, everyone. My name is Oren, and I'm with the Technion and NRCN. Here with me is Yehonatan Fridman, a researcher at the IEC and currently a master's student at the Ben-Gurion University. Today, we will present our comprehensive assessing work of the use cases of persistent memory in high-performance scientific computing. Scientific high-performance computing involves some main concepts of computational power, main memory, and storage. The advance in technology for each component is growing differently, creating significant gaps that impair the efficiency and fault tolerance of supercomputing systems. The computing power of supercomputers is increasing, and we are now entering the next era of supercomputing, the Exa-Scale era. The demand for computation resources increases, and more complex and powerful supercomputers are built to meet these needs. These graphs show the computational power in log scale of the top 500 supercomputers for each year, presenting an exponential increase in computational power over the years. You'll probably have heard about the Aurora supercomputer. Aurora is planned to be completed this year in the US and will have around 1 exaflops, providing enormous computing power. The supercomputers nowadays become more and more powerful, integrating heterogeneous hardware like CPUs and GPUs. The assembly of large supercomputers come with engineering difficulties. Our supercomputing systems become more complex, and with many more compute nodes, the probability of fault increases. Therefore, there is a growing need for a scalable and reliable fault tolerance mechanism that supports large-scale scientific codes. The common way today to support fault tolerance is by checkpointing the computational state of the program to a storage device and retrieve the last available checkpoint in case of a failure. But the storage performances is extremely low in comparison to the computational power of supercomputers and exhibit no significant improvements in technology over the years. Like HDDs and SSDs, all storage devices create a huge bottleneck to scientific applications, creating a significant gap that scientific computations suffer from. There is also a gap between the storage and main memory hardware in certain aspects. As storage devices have very large capacities, the DRAM capacity is very limited. However, the main memory introduces better performances than that of storage, about 2 to 3 orders of magnitude. But main memory is volatile and cannot serve as persistent storage to applications. Also, the storage cannot serve efficiently as an expansion to the main memory, as its access latencies are extremely high. The DRAM technology made progress over the years. The common used technology today is the DDR4, introduced in 2011. After a decade later, the world's first DDR5 DRAM chip was officially launched last year. The next supercomputers are planned to integrate this new hardware. DDR5 has about the same latency as DDR4, but is targeted to double the bandwidth and reduce power consumption. Despite these advances, DRAM's performances are still low in comparison with the growth of computational power. The DRAM is also very expensive and limited in capacity, creating a significant gap with the increasing demand for computational power. Putting all those concepts in one graph, we say that the storage technology evolves very slowly, introducing very large capacities of non-volatile memory, but with significantly low performances. As we said, 2 to 3 orders of magnitude are between the performances of DRAM and storage devices. The DRAM's technology advances over the last decades increases, but its performances are still way behind the computational power increase. These unbearable gaps brought to the emergence of non-volatile memories and their integration in next generation of supercomputing systems. The Aurora supercomputer, for example, is planned to consist NVRAM. Non-volatile RAM technologies aim to fit this gap between DRAM and storage. Intel Optane DataCenter persistent memory, or in short, DCPMM, is an emerging technology of non-volatile media. It is biodirectional like DRAM, but the data stored on the DRAM can be retained when the system is shut down or loses power. In addition, DCPMM comes in vastly larger capacities than DRAM. As you can see on the pyramid, the persistent memory creates new tier between the standard storage devices and the volatile memory hardware. DCPMM are priced in accordance with their market positioning, well above regular SSDs, but well below DDR4 of the same capacity. Persistent memory aims to have memory-like performances, but still there is a certain gap. For example, Optane's bandwidth on write operation is about 8% of that of DRAM. In this work, we explore whether and how DCPMM can close the gaps that are introduced in high-performance computing systems. We focus on certain use cases that Optane may be beneficial and are not focusing only on the raw performances of this new hardware. Now let's talk about HPC typical setting. A typical HPC environment for scientific computation consists of a large number of compute nodes that can communicate with each other via a network, for example, via InfiniBand. A single calculation often spans over a relatively large number of compute units. Each compute node contains multi-core processors and DRAM as main memory. The compute node have access to external distributed storage. Huge amount of data should be analyzed and manipulated in main memory and stored in non-volatile memory. Running large simulations can take a quite long time. Hence, recovery after failures may be very painful in complex systems that tend to crash frequently. So planning a computing system that can naturally provide efficient recovery to applications is imperative. One main way to deal with crashes is by storing checkpoints along the program's computation and recovering if a failure occurs. However, persisting new checkpoints to standard storage devices is very inefficient. HPC simulation, which carry out their checkpoint restart functionality in conventional storage, suffer from a performance penalty for performing a checkpoint. Putting out the weaknesses of HPC systems for scientific computing, we first know the DRAM limitation. DRAM is expensive and limited in capacity. As already said, scientific computations usually require analyzing and manipulating large amount of data. Therefore, in order to support large computations, two common solutions can be applied. The first one is distributing the computation data to several compute nodes. This comes with communication overheads. The second solution may be paging, which swaps the contents to or from the primary memory with the secondary storage. This is very inefficient due to kernel engagement and high latency of storage access. The second weakness we point of HPC for scientific computations is the storage. Scientific computations often write and read huge amount of diagnostics and perform checkpoint restart with huge checkpoints. Since storage devices like HDDs and SSDs are much slower than DRAM, they create a main bottleneck to the computation. This weakness harms the efficiency of checkpointing. Now, back talking on the Optane, Optane can be configured in two modes. The first mode is the memory mode, which in this mode, DCPMM acts as a volatile system memory under the control of the operating system. So no changes in software or application are required. It is transparent to applications. Any DRAM in the platform acts as a cache working in conjunction with the DCPMMs, together creating a large pool of volatile memory. The second mode is UpDirect mode, which in this mode, memory is persistent. DCPMM capacity is used as a byte addressable persistent memory that is mapped into the system physical address space and directly accessible by application. This is called DAX, direct access. Note that the DCPMM can be configured in mixed mode, where a percentage of the DCPMM capacity is used in memory mode and the remainder in UpDirect mode. So the following question arises. How can we exploit Optane DCPMM to improve scientific computations performances and fault tolerance in HPC systems? The first way Optane can be adopted in scientific HPC is for main memory expansion. The latency of DCPMM is almost as fast as DRAM's latency. So providing large capacities of volatile memory, Optane in memory mode may allow scientific applications to run larger problems, partially replacing the need for expensive paging or distributed computations. The second way is for faster non-volatile storage. As we stated before, in app-direct mode, Optane provides persistence, allows byte-addressable access to non-volatile memory. With the usage of persistent memory-aware file systems, scientific applications may efficiently write-read diagnostics and also save and restore checkpoints. The Optane seems to provide efficiency in certain aspects of HPC, leveraging scientific computing's performances. But how can we assess Optane's capabilities to improve performances of scientific applications? We suggest 3 use cases. The first use case is using NVRAM to expand a node's main memory, providing larger pool of volatile memory for applications. To evaluate Optane's benefits in this use case of memory expansion, we perform the execution of scientific benchmark with increasing memory usage beyond the DRAM's capacity. The second use case is using NVRAM as a fast local storage area for scientific applications. To evaluate Optane's benefits in this use case, we perform the execution of an IO-intensive scientific benchmark to evaluate the performances of Optane for reading and writing diagnostics. The third use case is using a combination of NVRAM and DRAM for implementing a fast internal and external checkpoint restart mechanism. In this use case, the NVRAM serves as a fast persistent storage and is used to load the memory image of the application into the RAM. To evaluate Optane's benefits in this use case, we perform the execution of a scientific benchmark with checkpoint restart. We persist the state of the computation along the program's computation to the Optane non-volatile memory and read back after a crash occurs. We consider external checkpoint restart as well as internal, as will be explained later. All of these use cases we examined should simulate the needs of a typical scientific application in an HPC environment and should give us a comprehensive image of the Optane's capabilities to fulfill these needs. Now let's dig into more details and see what we figured out. Yehonatan, please.
Thank you, Gal. So now let's talk about scientific benchmarks. What scientific benchmarks can we use for these suggested use cases? The NAS parallel benchmark suite is a small set of programs targeting performance evaluation of highly parallel supercomputers. These benchmarks are intended to emulate real-life scientific calculations and their usage of mathematical solvers. Among them are the BT solver, which stands for block tree diagonal solver, the LU for the lower upper Gauss-Seidel solver, and CG for conjugate gradient. The polybench benchmark suite consists of 30 numerical computations. These computations are extracted from various application domains, including linear algebra, data mining, and stencil computations. A prominent benchmark from the NAS suite is the BT solver, simulating a computational fluid dynamics application. Its solution is derived by solving 3 uncoupled systems of equations. These systems are composed of block matrices given in a block tree diagonal form. The BTIO benchmark presents a block tree diagonal partitioning pattern and benchmarks the IO patterns used by the BT benchmark. The figure on the right shows an illustration of data partitioning pattern for 9 NPI processes of BTIO. We choose to focus on BT and BTIO as they exhibit patterns of massive communications between processes and intensive I/O. Our experimental environment in this work consists of a single computation node having 2 sockets. Each socket contains a multi-core processor of 10 cores. The entire node contains 192 gigabytes of DDR4 DRAM and 1 terabyte of Optane DCPMM. The right figure describes the memory population of the entire node. Each socket has 6 DIMMs of DDR4, each of 16 gigabytes, and 2 DIMMs of DCPMM, each of 256 gigabytes. We note that there are several ways to arrange the DIMMs, and according to several previous works, this different arrangement of DIMMs can affect performances. However, in this work, we do not deal with this issue and take this specific arrangement as given. Now, back to the first use case that we suggested. For this use case of main memory expansion, we executed some representative benchmarks from the polybench suite. These calculations are taken from linear algebra, including several kernels and applications, data mining like covariance computation, and stencil computations like Jacobi kernel. We executed the computations twice. Firstly, with Optane in memory mode to expand main memory, and secondly, with swapping to a local SATA SSD device to support large virtual memory. The x-axis stands for the memory usage in gigabytes, and the y-axis stands for the performance in terms of floating point operations per second. The calculations were limited to the resources of one socket. The dashed vertical lines on the graphs represent the DRAM limit, which is 96 gigabytes, the DRAM capacity of one socket. To generate different memory usage sizes, the sizes were changed manually in the code. As can be seen in the results, before crossing the DRAM limit, performances are approximately constant in both graphs. When DRAM limit is crossed, performances decrease only by a factor of 2 to 3 when using Optane for primary memory expansion, while they deteriorate by 2 to 3 orders of magnitude when using memory swapping to a local SATA SSD. The NAS suit was also executed on our experimental environment, this time spanning the whole node's DRAM, which is 192 gigabytes. We executed different problem sizes according to the well-defined classes A, B, C, D, and E. As well as in Polybench, computations of NAS that fit into the DRAM leads to the quite same results in both graphs with approximately constant performances. After passing the DRAM limit, however, the performances decrease in the same pattern we observed with Polybench. The conclusion is clear. Optane's memory expansion enables running much larger problem sizes with the expense of only a few factors of increase in performance penalty. Now let's talk about the second use case of fast persistent storage for scientific applications. In our work, we focus on the most convenient and encapsulated ways to use the NVRAM so no massive changes have to be inserted into existing scientific codes. Persistent memory file systems, in short, PMFSs, meet this requirement and provide applications direct access to non-volatile memory. Local persistent file systems include X4, XFS for Linux-based systems, and NTFS for Windows-based systems. They support the special mode called DAX, direct access, that enables memory mapping directly from the NVRAM to the application memory space. This bypasses the kernel, the page cache, the I/O subsystem, avoids interrupts and context switching, and allows the application to perform byte-addressable load and store memory operations. For the second use case of reading and writing diagnostics, we examine the PMFSs SplitFS, NOVA, and X4 DAX. We choose to benchmark BTIO as an intensive I/O scientific calculation. The following graph shows the results of BTIO with MPI/I/O write workloads. The x-axis stands for the total I/O amount in gigabytes, and the y-axis stands for the bandwidth in megabytes per second. The orange trend shows the bandwidth of writing to a local SATA SSD device under the XFS file system, while the other trends show the performances of writing to obtain non-volatile memory under SplitFS, NOVA, and X4 DAX. We modified BTIO to execute a file sync after every write to ensure the immediate transition of data to the Optane and to the SATA SSD. The results show an improvement of 3 to 4 factors of I/O performances when using Optane DCPMM in respect to SSD. This graph shows the results of BTIO for read workloads. We observe an improvement of up to 10 factors in read workloads performances with Optane DCPMM. The conclusion is clear. Optane DCPMM dramatically increases I/O operations as a fast local storage area for scientific applications. So, after we saw good results with local PMFSs, now we want to talk about distributed file systems. Scientific computing applications usually require a distributed PMFS that operates on several nodes. Distributed PMFSs control how data is stored and retrieved from NVRAM when accessed by more than one node, using communication such as Ethernet and RDMA. Octopus is a distributed file system that closely couples NVRAM and RDMA in order to reduce memory copying overhead. Unfortunately, we found Octopus incompatible with Intel's Optane since it manages its storage space on an emulated persistent memory of Linux in each server. ASYS is a DFS based on a persistent replicated coherence protocol. Its main goal is to support work over several types of storage media, like RAM, SSD, HDD. We found that ASYS is incompatible with MPI implementations such as OpenMPI, and its system call interception mechanism collides with that of DMTCPs, which is widely used for checkpointing scientific applications. DAOS is designed from the ground up to support storage class memory and NVMe storage in user space. At the same time, DAOS provides POSIX access for legacy applications, as well as direct MPI I/O and HDF5 support. Further work should be done in assessing the performances of the state-of-the-art DAOS in the context of scientific distributed applications. For the third use case, to evaluate the performances of checkpoint restart with NVRAM, we introduced transparent and explicit checkpoint restart to the BT benchmark from NAS benchmarks. There are two ways of conducting checkpoint restart: transparent and explicit. In transparent checkpoint restart, the state of the program is saved without any knowledge of the application or intervention from the programmer. A possible implementation of such approach might be based on checkpointing in the user space by catching and wrapping any needed system calls in order to continually track the state of the program application. An example for transparent checkpoint restart library is the distributed multi-threaded checkpointing library, DMTCP. To perform a checkpoint, the library synchronizes and coordinates between the parallel computation processes, captures the system calls, and saves the checkpoint locally. When researching the processes, the library loads the checkpointed processes into memory and coordinates them before resuming the run. In explicit checkpoint restart, in order to successfully checkpoint and restart a program from a valid state, the program has to store the whole required computational state. For scientific simulations, this usually consists of the data and the current timestamp. An example for explicit checkpoint restart library is the scalable checkpoint restart, SCR. A simple flow in an SCR library would be as follows: check for recovery and recovery state if needed, proceed with the program execution, and update with the latest checkpoint. We apply the transparent and the explicit checkpoint restart to the BT solver of NAS. In the explicit checkpoint restart case, at the end of each iteration of the computation, we persist the benchmark state. That includes matrices, the iteration ID, and some auxiliary data. In the transparent checkpoint restart case, for a fair comparison, we implemented a DMTCP plugin that synchronizes the checkpoint execution at the end of each iteration. We applied both DMTCP and SCR checkpointing to a local SATA SSD device and to the Optane DCPMM. The right graph shows the storage utilization of DMTCP and SCR checkpoints in an increasing number of processes. As expected, when using DMTCP, the storage utilization is greater, about 2.5 times than that of SCR, as the checkpoint of DMTCP involves more information. The left graph shows the runtime of BT in a crash-free computation. The blue line is for the original BT execution with no checkpoints. The orange and green lines represent the runtime when conducting checkpointing to SSD. The red and purple lines represent the runtime with checkpointing to the Optane. The results show that SCR performs better than DMTCP, but both perform better on NVRAM than on SSD. The middle graph shows the computation time in per iteration perspective. Each column presents the breakdown of recovery, checkpoint, and compute time in a single crash computation. The red part is for the checkpointing stage, the blue is for the recovery, and the brown is for the iteration computation. As the results show, checkpoint restart on top of NVRAM shows shorter checkpoint duration both on DMTCP and SCR. In addition, SCR demonstrates faster checkpoint and recovery durations compared to DMTCP. So, for conclusion, future Exa-Scale supercomputing systems will incorporate non-volatile memories. An example for such an HPC system that includes Intel DCPMM is the Aurora supercomputer. Our results show that in all the suggested use cases, DCPMM exhibit outstanding performances. DCPMM allows to expand the byte addressable memory at the expense of only a few factors of cost. DCPMM also drastically improves access time to persistent storage in comparison to SSD. DCPMM facilitates checkpoint restart greatly. We conclude that Optane have the great capabilities and potential to close the gaps introduced in high-performance computing. We conclude that next generation of supercomputing systems might be able to avoid the use of standard storage completely and to adopt non-volatile memories for better performances as well as for higher fault tolerance. Thank you.